Somewhere out there, right now, two planets are dying in real time. Not exploding, not colliding. Something slower, stranger, and in its own way, far more disturbing. Entire worlds made of solid rock are being scorched apart by the very stars they orbit, spilling their own melted interiors out into space in glowing, comet-like tails visible from 25 light years away. Scientists studying the data have used one specific phrase to describe what they're witnessing: utterly cataclysmic. And for the first time in the history of astronomy, we're not just detecting evidence that this kind of planetary death happens somewhere in the universe. We're watching it unfold, piece by piece, on two separate worlds at the exact same time. This is the real story of what James Webb actually detected, how astronomers know these planets are genuinely disintegrating rather than simply orbiting closely, and why researchers are calling this a uniquely valuable, almost impossible opportunity to study something we could never otherwise see. Let's start with the first of these two worlds, because the story of how it was found is itself a genuine scientific detective story. The planet is called K2-22b, and it orbits its star at a distance so close and at a speed so fast that a single year on this world lasts less than 9 hours. That extreme proximity to its star means K2-22b is being baked at temperatures intense enough to do something that shouldn't be physically possible for an ordinary rocky planet to survive. Its own solid surface is evaporating. Rock, the same basic material that makes up Earth's own crust and mantle, is being vaporized directly off the planet's surface by the heat of its star. And that vaporized rock is streaming away from the planet in a long, comet-like tail, visible in astronomical observations as a genuine physical extension of the dying world itself. When a research team, led by Nick Toucey at Penn State University, pointed the James Webb Space Telescope at K2-22b to study that evaporating material in detail, what they found immediately puzzled them. Webb detected gases, including carbon dioxide and nitric oxide, streaming away from the planet, chemical signatures that, on the surface, made no obvious sense. Those specific gases are typically associated with icy bodies, comets, and similarly cold, distant objects, not with the mantle of a scorching, close-orbiting rocky planet where any ice should have evaporated away and been lost to space long ago. Toucey described the reaction to that unexpected result in blunt, honest terms. It was, he said, a genuine "who ordered that" moment, the kind of finding that doesn't fit neatly into an existing explanation and forces researchers to reconsider their assumptions. The explanation Toucey and his colleagues eventually proposed connects directly to the planet's own history. They suspect K2-22b may not have originally formed anywhere near its current scorching orbit at all. Instead, the planet likely formed much farther out from its star, in a colder region of its solar system where ice could genuinely exist and persist before gravitational interactions, disturbances caused by other objects in the system, gradually pulled it inward over time. That kind of gravitational perturbation, the researchers note, shouldn't be particularly uncommon in this specific case, given that K2-22b's host star actually shares its cosmic neighborhood with a companion star, adding exactly the kind of additional gravitational complexity that could plausibly nudge a distant, icy planet onto a slow, inward migration path over millions of years, eventually delivering it to the hellish, close orbit where we now find it. Its ancient ice long gone, its solid rock now taking ice's place as the material actively boiling away into space. That discovery alone would already be remarkable. But K2-22b isn't the only world currently caught in this exact process. And the second example comes from an entirely separate research effort using a different instrument altogether. Using NASA's Transiting Exoplanet Survey Satellite known as TESS, a separate team of astronomers identified another disintegrating exoplanet, this one named BD+ρ5 of 4868ab, orbiting a different star entirely. This second world holds a genuinely significant distinction of its own. It's the closest evaporating exoplanet to Earth ever discovered, making it an unusually accessible and usually well-positioned example of this same rare, violent process happening to a nearby star system. What TESS's data revealed about BD+ρ5, 4868ab, is, if anything, even stranger than what Webb found at K2-22b. This roasted world doesn't have just one tail of escaping material trailing behind it. It has two distinct tails, each with a completely different physical character. A leading tail extending out ahead of the planet along its orbital path, made up of larger, sand-sized particles of evaporated rock, and a separate trailing tail following behind the planet, composed instead of much finer, soot-sized grains. Together, according to the research team's measurements, these two tails span a genuinely staggering distance. 6 million miles, roughly 9 million kilometers, together occupying almost half of the planet's entire orbital path around its star. That's not a small, subtle wisp of escaping gas. It's a physical structure large enough to dominate a meaningful fraction of the planet's own orbit, made entirely from the vaporized remains of what used to be solid planetary rock. Jason Wright, a professor of astronomy and astrophysics at Penn State, and a co-author on the research studying this kind of disintegration, described exactly why events like these matter so much to planetary scientists, despite, or perhaps because of, how violent and destructive they actually are. It's a remarkable and fortuitous opportunity, he explained, to understand terrestrial planet interiors. That statement gets at something genuinely important about why watching a planet die can teach us more than watching one quietly survive. Under ordinary circumstances, there's no way to directly sample what's inside a rocky exoplanet. You can't send a probe to drill into a planet 25 light years away. You can't collect a physical sample and bring it back to a laboratory. The only real information available comes from remote observation of the planet's surface and atmosphere, which normally tells you very little about what's actually happening deep inside. But when a planet disintegrates, when its rocky material actually evaporates directly off its surface and streams away into space where a telescope like Webb or an instrument like TESS can directly detect and analyze it, that process effectively hands scientists a sample of the planet's own interior composition, delivered to them across light years for free through the simple physics of extreme heat vaporizing solid rock. Studying the exact chemical composition of that escaping material becomes, in a very real sense, a form of remote geology, letting researchers infer what these planets were actually made of on the inside, information that would otherwise be completely inaccessible for any exoplanet, no matter how thoroughly studied by conventional means. That's precisely why researchers are describing this moment as genuinely elated, rather than simply alarmed or fascinated by the violence involved. Watching two separate disintegrating rocky worlds, studied simultaneously using two different powerful instruments in roughly the same window of time, represents an extraordinarily rare convergence of circumstances. Disintegrating rocky exoplanets are not common. The physical conditions required, a rocky planet orbiting close enough to its star at exactly the right combination of size, composition, and stellar heat to actively boil away rather than simply existing in a stable, if scorching, close orbit, represent a narrow, specific set of circumstances that most close-orbiting exoplanets don't actually meet. Finding one such world would already be scientifically valuable. Finding two, observable in enough detail to study their escaping material directly, represents a genuinely unusual scientific opportunity. It's worth being precise about the actual physical mechanism at work here, because disintegrating is a strong word that deserves a clear explanation rather than vague, dramatic language. These planets aren't exploding, colliding with anything, or being torn apart by gravitational tidal forces in the dramatic way a black hole might rip apart a passing star. What's happening instead is a slower, steadier process of thermal evaporation, similar in basic principle to how a comet's icy surface boils away into a visible tail as it approaches the sun, except happening to solid rock instead of ice, and happening continuously, orbit after orbit, as these planets remain locked in place close enough to their scorching host stars for that evaporation to persist indefinitely, or at least for as long as there's still planet left to boil away. Given enough time, potentially millions of years depending on the planet's size and composition, this kind of sustained evaporation could genuinely, eventually consume an entire world, reducing what was once a solid rocky planet down to nothing at all, its material scattered and lost to space in exactly the kind of glowing tail astronomers are now able to directly observe and chemically analyze. That eventual fate is part of what makes watching this process happen in real time feel so significant. We are not looking at a theoretical model of what might happen to a rocky planet under extreme conditions. We are watching actual physical evidence of exactly that process happening right now to two specific real worlds, close enough and clear enough for our best instruments to study the escaping debris in genuine chemical detail. The unexpected discovery of icy chemical signatures in K2-22b's tail adds an entire additional layer of scientific value on top of that, suggesting the planet's current doomed orbit isn't necessarily where it started its life, and that its slow death by evaporation may be the final chapter of a much longer journey that began somewhere colder, farther from its star, before gravity slowly, patiently pulled it inward toward the fate we're now observing. What makes a story like this worth taking seriously, without exaggerating it into something it isn't, is that the real science here is already dramatic enough on its own terms. Two separate rocky exoplanets, studied using two separate, powerful astronomical instruments, both caught in the genuine, ongoing process of thermal disintegration, one trailing a single comet-like tail of evaporated rock, carrying an unexpected, still being explained icy chemical signature, the other trailing two distinct tails of escaping debris, spanning millions of miles across nearly half its own orbital path. Nothing about that needs embellishment. It's a direct observed window into planetary death, And scientists studying it are explicit that the value isn't simply in confirming that such destruction happens somewhere in the universe. It's in what the escaping material itself can reveal about what these worlds were actually made of, deep inside. Information about rocky planet interiors that would otherwise remain permanently locked away, inaccessible to any telescope, for any planet that isn't currently visibly coming apart.